Okay, number of constitutional isomers that could have been shown. 2 DUS, 28 valence electrons. Hopefully some helpful information. How do we do? There's a chance that none of you showed those two there. There's a variety of answers. Octets, carbon with standard bonding, no carbons with 5 and 6 and 8 bonds, etc. What we got? Ketone and ester, yeah? 12 GUS, C was the strongest bond, is that right?
Yes.
21, did I get it right? No?
Yes.
I counted twice, how many?
I got it wrong.
Okay.
I got 21.
Nitrogen here is in an S, this lone pair is in an sp2 hybrid. This lone pair is in a p orbital, yeah? Yeah? That's the exception we talked about, so it's p orbital next door. This lone pair is said to be conjugated. It's in resonance. That lone pair is not conjugated. Only p orbital electrons in p orbitals are conjugated. This silicon is -1. Did I get it right? It'll be posted upstairs. You can shout out any questions if you like. Yes.
I got 20 for the hydrogen because I thought you subtracted 1 for the nitrogen. When I subtracted 1 for the nitrogen, I had to get.
No, that's when you're doing DUS. No, you don't subtract anything. I mean, hydrogens are there. As stated on the syllabus, you're supposed to put your course section on your quizzes. I'm not sure why there was difficulty there. Also, if you come in at the top of the hour when the quiz is being distributed, that's just way too late, and you're going to have to sort of just come on in and fend for yourself. I'd recommend getting here 5 minutes earlier, as stated in the syllabus, especially on quiz test day. Because I want to make sure that people are here, are not distracted as we begin. Okay? Again, to your benefit. We need to get going. Any questions about lab this week? We got the video for the distillation. Each of you will receive 2 unknowns, 1 liquid, 1 solid. Your mission, should you choose to accept it, is to identify both of them. IR will be used. In IR, did it say some students should use one IR, some students another? I don't think I've added that piece of information yet. I may send you an email. I may divide you up into thirds and say maybe students A through Z or whatever use this IR. That way you don't have to worry about being ready to use any of the 3 IRs. Okay. Class time is valuable. Let's get going. I think if I turn the light off, it's showing up better. Maybe that's what the difference is. We'll see how that goes. There's a handout here, nomenclature of alkanes by video. I sent that handout by email. There's lots of other stuff in the handout as well. Here's an outline that goes with the next information. The acid base is not really on an outline, it's just on this so-called handout. But it's sort of, its sections are sort of there. Any last questions before we get going? How are we doing with IR? Properties, acid-base chemistry. Here we go, very important. Hybridization effects, okay? 1 through 4, yeah? 1 through 4 is very important here. 1 through 4 physical process is very important. Bases. move on to bases. Before we do that, let me ask you, which one of these anions is most basic? What do bases want to do? What's the definition of a base? Bronsted-Lowry base, everything Bronsted-Lowry. Definition of a base. I heard two people say hydrogen acceptor. I'd recommend don't use that terminology, bad terminology.
It takes it from
No, bases don't accept, bases take. Okay? To me, it's much better if you understand that they take. Accept acts like they don't do anything. They just sit there and accept. No, they do everything. Please say take. I'll put you in the right framework to then understand what's going on. Bases take hydrogens. Okay? Which one of these is going to be most eager to take an H? By the way, when it takes an H, it goes neutral, or if it's neutral, it goes positive. Here they're negative. If these take an H, they go to neutral. Which one's more eager to go to neutral? The one that's most stable as an anion or least stable? Least. This guy he wants to go back to neutral. In fact, that's why that was more acidic. Because this guy doesn't mind being minus. So this guy's more acidic. It doesn't mind giving up the H. But this guy wants to go back. This guy wants the H. This is a stronger base. Okay? And we kind of know the thing that a weaker acid gives a stronger conjugate base, but you guys typically don't understand that because you want to consider, you don't know what the conjugate base is. You really need to understand what a conjugate base is and be able to show it. Conjugate base is going to be a stronger base for a given weaker acid. It's a stronger base because it's least stable. It wants to take an H and go back to neutral. Okay, so we're going to be looking at the same considerations, but it's just going reverse, and it's the opposite consequence. All right, some introduction to bases. Bases take hydrogens. Okay, I know we say accept. I don't know why they want to use that term. They take hydrogens. And usually hydrogen, we're talking about H+. Okay. It takes just the H nucleus, not the electron that the H may have been bonded with. For example, this carbanion can take the H from water. We did an acid-base mechanism, extremely important for understanding this. Every acid-base mechanism will be the same. The lone pair, you can circle it, the lone pair bonds to the H. The electrons that used to be bonded to the H move on to the atom that's bonded to the H. In generic, it may have been shown as a Z atom, some generic. Here it's oxygen. Electrons move on to oxygen. That's what you have. This is now bonded to the H. That's why we show that. These electrons now move on to oxygen and become the third lone pair. That's why we show that. And of course, charge, because that's charge. Okay? And of course, you all know that the conjugate acid-base pair, one's going to be neutral, one's going to be charged, right? You learned this stuff in Gen Chem. Okay? Charged, now neutral, neutral, now charged. If not, there's a summary page at the back, free information. You know, stronger bases will have a higher pKa for the conjugate acid, right? Okay, this will be largely reviewed. That's setting the stage. This is what I expect you to know in review. Okay, bases don't have to be anions. In my example, it was. Many neutral nitrogens are basic. All right, as we move forward, we'll talk about what are good bases. For example, are neutral oxygens good bases? Typically, no. The only thing that's good base in the neutral form is typically nitrogen, at least at the introductory stage that we'll be dealing with. Anything else typically has to be an anion. But many neutral nitrogens are basic. For example, we know ammonia is basic. Okay? The simplest amine you can have, the lone pair, takes the H. These electrons move on to oxygen the same way there. The nitrogen is now bonded to a fourth hydrogen. That's all shown condensed, but this is 4 bonds to hydrogen, right? Nitrogen's positive. We produced hydroxide. Now we need to talk about equilibrium. All right, I didn't talk about that up there because it's so far to the right. Equilibrium is described by pKa's. We know that we're going to have a pKa for each acidic species in our equilibrium. Over here, what's the acid on this side? The acid is the thing that contains the H. Water. What's the acid over here? Ammonium. It's now the acid on this side. It's the conjugate acid at the base. Okay? The H is like the hot potato. It gets bounced back and forth. This is the acid over here. This is the acid over here. We can give a pKa of each of these. Again, mostly review. All right, let's look at determining strength of bases. Again, the same considerations, 1 through 4, but we got to figure out the consequences of those things. Which is a stronger base? Neutral nitrogens tend to be basic, particularly if they're sp3. Let's write this. If the lone pair is in an sp3 orbital, okay? sp2 LP slightly basic. An sp lone pair is getting half of slightly basic. Weakly basic. sp3 lone pairs of nitrogens tend to be pretty good bases. Like right here, this lone pair is in an sp3 orbital, right? Well, so is that one, so there's no difference here. What's the difference in these molecules? Obviously the method. What do we know about the electronic properties of a methyl? Just a plain sp3 carbon. What do they do electronically? They donate electrons. We stated that last time. I told you it's a very important tenet of organic chemistry. They donate electrons. Okay? So which one's going to be more basic? Well, if the lone pair is going to do something and take the H, we're talking about, why would it take an H? I mean, this is bonded to some type of electronegative atom, right? Chlorine, oxygen, partial plus. Well, these are electrons. They have minus charge. Minus is going to be attracted to the H. And you get that magical bonding that takes place. Again, the book that thick. And every acid has this. The difference comes from, well, how much minus is here? Okay, is every lone pair the same? Or would the presence of this donation make this be more minus? This is like electricity here. Or you can talk about maybe your bank account of electrons. Which has a higher bank account of electrons? One over here with a rich friend donating money. Higher electron density because of the electron donation. Higher electron density here in this region is going to make this more minus and more attracted here. This is a stronger base because of the inductive donation of the sp3 carbon. Okay? So of our 1 through 4, this is an inductive effect, right? That's why that's more basic. Number 2, which is more basic? We already know the answer to this based on what we wrote over there. But forget about that. Let's think about it more broadly. This is really a hybridization effect. Because this lone pair is in an sp3 orbital. This lone pair is in what type of orbital? That one's in an sp2. And based like what we said over there, which one's more basic? Yes. This one's more basic. But now let's answer why. Why is that more basic? Can anybody explain why a lone pair in a sp3 hybrid would be more basic? Why would it be more eager or available to go react with this proton? Or, on the other hand, why would this one be less eager and available? What do we know about the positioning of the long pair of the orbitals? Size of the orbitals. This is a longer orbital. So the electrons are on average further away from the nucleus. Okay? Here's the proton. Okay? Here I am. I got my lone pair like this. Let it go here. Lone pair like this. Well, I just can't really get there. How about my lone pair out here? Boom. Also, closer to the nucleus, there's less just pulling this way, more attraction towards the nucleus. These electrons are held tighter to mama, tighter to the nucleus. These electrons are more out there, available to react, both with a proton and with just about any other thing we do down the road. This lone pair is more reactive. It's a hybridization effect. But the type of orbital you're in, the electrons are in, affect the reactivity, basically because of this versus this. These electrons are less reactive. They're held tighter to the nucleus, more basic. That's why the trend sp, what if the lone pair was an sp? Even tighter to the nucleus, because that's 50% s. Lone pairs in an sp, they become just marginally basic, really not basic at all. 3. Again, these are neutral. Typically nitrogen. That oxygen is neutral. It has a lone pair. Neutral oxygens tend not to be basic. Why? Let's compare this lone pair to like ammonia lone pair. Well, you got a difference in hybridization, but here you got a difference in electronegativity. If everything else is the same, even the same hybridization, oxygen just inherently holds it tighter, even if it's in the same type of orbital. Where nitrogen inherently doesn't hold the electrons as tight. Oxygen's a better parent. Nitrogen lets its lone pairs get out there and do things. Okay? Typically for an oxygen to be basic, it needs to be an anion. Only neutral nitrogens tend to be basic. Let's focus on the nitrogens. Which nitrogen's more basic? This lone pair is in what type of orbital? sp3. Hopefully you're getting used to these condensed things. This is a nitrogen with bond to H, and bond to carbon. Right? You know the H is not between the H and the carbon, the end of the carbon. It's condensed. This lone pair is in what type of orbital? P in p orbital. Yeah? Anytime a lone pair is next to a p orbital, going to want to be in a p orbital, especially when it looks like it's sp3, but it's actually sp2. The nitrogen's sp2, but the lone pair is in a p orbital. And lone pairs that are in p orbitals are not basic, except for a few minor exceptions where we can explain that. Starting point is lone pairs in p orbitals not basic. Because it's in a p orbital, busy doing what? Interacting with the next door p orbital. This lone pair is not interested in interacting with this atom. It's got something to do. It's interacting with the next door orbital. It's busy. It's distracted. It's not interested in being a base. Okay? This is basic. You can call that a hybridization effect. But it's not exactly, because you can have two nitrogens that are both sp2, but this one, the lone pair, may be in sp2, this one, the lone pair, may be in p. So the overall hybridization doesn't always give you the answer. Look at the lone pair. How about some anions? Which one's more basic? F minus or Cl minus? Kind of look at it like we did up there. Which one's more stable? Cl minus is more stable because it's bigger. Charge is more spread out. So which one is most eager to take an H and go back to neutral? F minus. It's least stable. It wants to go back to neutral. With anions, that's the way I typically will approach. Which one wants to go back to neutral more eagerly? It's a little counterintuitive because we know F is the most electronegative. It should like being minus, right? But we know that size thing is important. And actually, that's more stable. F minus, like, I don't want to be minus. Can I go back to neutral? Which one's more basic, ammonia or water? I already really answered this over here. Neutral nitrogens tend to be basic. Neutral anything else, typically not. All these lone pairs are sp3. But because the atom or the nucleus is different, sp3 for oxygen is like this, but sp3 for nitrogen is like that. Oxygen's a better parent. And water is just not, do you consider water a base? Here's a caveat. Anything with a lone pair can act as a base. That's where we have to kind of learn the nuances. Can water act as a base? Sure. It's got a lone pair. But is it a good base? No. That's why we don't call water basic. Oh, okay? So there's a nuance that we have to just sort of... Which is a better base? Really, we answered at the top, not directly, because that was hybridization. Which is a better base? Carbon. Of course, a neutral carbon is not going to be basic, because usually neutral carbons don't even have lone pairs. But carbanions can be basic and pretty strong, because carbon doesn't like being minus, really. But which one is more basic? What's the difference? More sp3 carbons? More donation? Which one has more electron density at the business end? This one. Okay? All right. This is an inductive effect again. Donation makes this more electron rich compared to this. More electron rich wants to be more physically attracted to the partial positive, but also in the lingo, this really wants to go back to neutral more than this one. Because lots of electrons is not good. Things tend to want to be neutral. All right? This guy really wants to get back to neutral more than the other. Any questions about those? We use the same arguments, 1 through 4, but we're understanding that the bases are going the opposite way. Questions about those? Neutral nitrogens can be basic. You ever heard of the term alkaloids? These are compounds that are found in nature that contain basic nitrogens. You ever heard this in biology? Alkaloids? You know any alkaloids? Other than those on this page? Morphine? Cocaine? Morphine, kind of a complex structure. It's got a ring that comes from 2 other rings sort of bonding and making a ring. But look right here. That nitrogen's basic. Lone pairs in an sp3. sp3 lone pair, basic. All these contain a basic nitrogen. And these act as bases in nature. Okay? property of the molecule is also heavily influenced by the presence of a basic nitrogen. Okay? So they have some alkaline type properties. We know hydroxide is alkaline. Alkaline meaning basic. It's not strongly basic, so it's like alkaline-like, or alkaloid. Like a humanoid. Not quite human, but these are not quite basic. They're pretty decent, though. Some interesting ones on there. Equilibrium. Now, I know you guys have spent lots of time on this in the previous course. Let's look at it in the context of organic chemistry and sort of boil it down to what you need to know and how to work with it here. Predicting equilibrium. Well, we know reaction will favor the side of the weakest acid, right? You all know that. I think I showed this on previous page. This reacts with water to make methane plus hydroxide. Equilibrium lies to that side. By how much? 10 to the 25, right? Right? To predict this, you have to know pKa's. What's pKa of water? I tell you it's about 16. Some books will say 14.5. It's all the same in the ballpark. I mean, 14.5 versus 16, that's okay. 16 for me. Need to know that, yeah? There's a list of pKa's in the back of the lab manual. You don't need to know them all, but we need to start just getting familiar with some. Certainly at this point, you need to know water 16. Hydrocarbon, not that acidic. But this is the conjugate acid, right? So we need to look for the pKa over here. pKa greater than 40. Look at the pKa list. It sort of explains the relative Y each time. Why? Because the conjugate base would be that. That's not that stable, so this ain't going to act as an acid. Very poorly acidic, so this has high pKa's. These are your two pKa's. We know the equilibrium lies to the side of the weakest acid. This is the weaker acid, right? Much weaker than water. Lies to this side. How much? Difference in your pKa units. 10 to the 24, right? By the way, how much is 10 to the 24? Like 100 gazillion, right? At equilibrium, you have 100 gazillion of these and only one of these. That's pretty much favored. Do you agree? Turn that into a percentage, it's probably 99.9999999% of this, and the remainder of this. I would call that complete. If you don't want to call that complete, then nothing is ever complete, because it's a huge number. But all that you know, right? That was all Gen Chem, equilibrium, using pKa's. Anything new? Hopefully not too much. Let's put this in practice. Acetic acid, pKa of about 5. You should know this one. Carboxylic acid is the only functional group that's called an acid. pKa of about 5. We can show it reacting with water, just like that reacted with water. First off, I'm giving you the answers of what's formed. Later on, I will expect you to provide this on your own. Okay? Well, we can show this plus this. Here, water acted as a what? Acid or base? Acted as an acid because this took the H. That's the base. It took the H. Water supplied the H. Acid supplied the H. Right? That was the acid. But down here, how's water acting? Down here, water's acting as the base. Because down here, water's taking the H. We can get this and this. pK of acetic acid is 5. What's the acid over here? That is, if I could draw the proton in green, there it is. Where's it at over here? Well, now it sits with here. I mean, one of those is green, the other two is not. That's the H that's getting transferred. This contains the H over here, so that's the acid over here. What contains the H over here? Yeah, that's the what's the pK of hydronium ion? Not water, it's protonated water. That's less than 0. Some books will give it a number. Less than 0 is fine. Which side's favored? 5 or less than 0? Weaker acid's favored. 5 is favored. This side is favored. Okay? How much is this side favored by? 10 to the 5. Now that's a number that what is 10 to the 5? That's 100 is 1,000. What's that? 100,000? 10 to the 5 is 100,000. That means in equilibrium we have 100,000 of these and one of those. Question, is water a strong enough base to fully deprotonate acetic acid? Deprotonate, remove the proton. Will water fully remove the proton? Will it react with this and go over here completely? We just said no. It will only do it 1 out of every 100,000. That's nothing. Water is not strong enough to do this. Right? But you know that you put this in water, you do get some ionization. But guess what? Only 1 out of every 100,000 ionizes. That's pretty weak ionization, right? That's why we call it a weak acid. 99.99% of the molecule remains fully covalent, not ionized. Okay, here we go. Example problems. Show the result of this acid-base reaction. Also predict which side is favored and by how much is that side favored. Same thing with the rest of these here. Let's do this one here. Let's give you 30 seconds, see if you can do that here. Show the result of this acid-base reaction and then predict which side's favored, etc. Okay, here we go. This one's a little more simplistic to some degree. Which molecule is the base? Hydroxide. You know that's base, right? It could act as an acid, but base. I'm giving you a pKa for this. That sort of implies it's an acid. If this is a base, okay, do your acid-base reaction. We know it's a base. Over here, we know this is the acid. But which hydrogen is the acidic hydrogen? Because we have the hydrogen on nitrogen and we also have hydrogens on carbon. 4 of them. Which one is most acidic? Last lecture we talked about ways to determine that, right? Which one's most acidic? One on nitrogen. Hopefully you know why. So, now that you know this is the base and that's the acidic hydrogen, I'll show you your outcome. Highly recommended that you employ the acid-base mechanism, which works for every single acid-base reaction in the world. Bronsted-Lowry. What is that mechanism? The electrons of the base do what? Bond to the H. What happens to these two electrons? They move on to the nitrogen. There's one lone pair there originally. I'll show the outcome. Hydroxide is now bonded to the H. That's what this arrow means. How many lone pairs remain on the oxygen? 2. Because the other lone pair is bonded to the H. And lo and behold, what's that? Water. What else do we get? Well, we got the nitrogen. Nothing happened here. One lone pair originally. What else is now on the nitrogen? What does this arrow mean? The 2 electrons of the bond moved on to the nitrogen as a lone pair. So now it has a second lone pair. But that ain't a typical nitrogen. We need to be looking for charge. What's the charge of that nitrogen? 2, 4, 5, 6. It owns 6, but it's only supposed to have 5. It's got an extra one. Yes, it's an anion. And lots of things are here. Please check the very last free information sheet. For example, every conjugate acid-base pair, neutral charge. This one's neutral, so we know that the conjugate's going to be charged. Charge neutral. Here we go. How do we predict? pKa here is 8. What's the pKa of the acid over here?
16.
Well, this is the acid. It contains the H. It's 16. Which is favored, 8 or 16? 16. Weaker acid, which is this. Favored by how much? Favored by 10 to the 8, which is what? 100 million. At equilibrium, you have 100 million of these and only one of these. Question, is hydroxide strong enough to fully deprotonate this guy?
Yes.
Well, 100 million to 1 sounds pretty full and complete to me. Turn that into a percentage, it's 99.9999999% this way. Hydroxide converted this 99.99999% to this. Yes, it's strong enough. Please do the ones below. Let's see what type of questions came up, because there's a few other twists in there. And then we'll be looking at how pH comes into play. Henderson, Hasselbalch. We'll finish this up and we'll be moving on to the alkane handout on Wednesday. Please have that handout here with you.